Alright, for our final unit, Unit 4, for the spring 2015, we're going to be talking about the last three chapters in our book, chapters 16, 17, 18. We recently got done talking about radical reactions and also talking about, in chapter 11, activation of alcohols and also oxidations. So now we're going to finish kind of our last set of functional groups. We're going to talk about carboxylic acids, so C double bond O's, right? Essentially carbonyls. In this particular, we're going to talk about carboxylic acid derivatives. Chapter 17 talks about aldehydes and ketones, and then 18 goes a little more into synthetic versions of these. So let's divide these families into groups. Basically, the big difference here is these are carboxylic acid derivatives, where Z is an atom that's more electronegative than carbon. So examples would be oxygen, an OH, an OR, a carbon like an ester, so a carboxylic acid here, an ester here, an amide. An amide would be a possibility. A chloride, an acid chloride. We can even have anhydrides. Nitriles are considered a derivative of carboxylic acids as well. The other type that's not in chapter 16 are Z here, right? Z is just a designation. So all these are derivatives of carboxylic acids. Z here being R and H, which would basically mean either a ketone or an aldehyde, right? So basically that's saying these can all be turned, or are, either can be turned into or are good leaving groups. Carbon and hydrogen are never going to be good leaving groups. That's the big difference. So we'll focus on these first. Similarities: the carbon of the carbonyl group is always delta plus. How delta plus is it depends on what's attached. But the carbon of the carbonyl is the electrophilic site always. So we do a little bit of nomenclature here. Go through this kind of fast. Again, nomenclature, how much we need to know is, enough to identify these things. C double bond O is called the carbonyl group. There's many different types of carbonyl groups. An acyl group is a carbonyl with an R group, which would be a carbon group. This is an acyl group. So generally speaking, we're talking about carbonyls. That's a C double bond O. And a particular type of carbonyl is an acyl. Again, breaking these down, these classes of carbonyls, this is in your class notes. And the biggest thing is here, they do not react all the same way. They don't react the same way. Right? And we wouldn't expect them to. Right? An OH is different than an OR, which is different than a chlorine. Right? If we think about a chlorine as a leaving group, right, a Cl minus, we would say is much more stable than, say, an NH2 minus as a leaving group. So that's the things we got to be thinking about when we understand how these react. And even more so, carboxylic acid, it can react as an OH. So there's a lot of things to think about. But all of these groups, the OH, the OR, the Cl, and these nitrogens, these amides, can be replaced by a nucleophile. And that's the key, right? Versus before, when it was just a carbon or an H, those are not good leaving groups. These can be leaving groups. So they can be substituted. Now the mechanism will be a little different than we've done before, but they can be substituted. So here are the other classes, the other H and R, right? These cannot be replaced by a nucleophile, right? Because H minus or R minus or C minus, they're not very good leaving groups, right? A good leaving group is something that's stable, right? We've seen the leaving group hierarchy before. H minus and C minus would not be very stable. They would not be very good leaving groups. Right? So all those ones before, the OH, the OR, the Cl, all the amide, NH minus, are good enough leaving groups to be replaced by a nucleophile. But again, it's a substitution, right? It's a substitution, but right, it's going to be different. So these ones do not have a good enough leaving group. So we'll wait till chapter 17 and worry about the aldehydes and ketones. Now here's a table that's in your book, and again, they're talking about basicity, which I think can sometimes get confusing. Just remember what you know, right? So here are the numbers of pKa, basically saying pKa tells us how good of an acid something is, right? So none of these are acids. They all have negative charges. They're talking about basically their conjugate They're conjugate acids. So these are all bases. But basically what this is telling us is Cl minus stable. Yes, it's a more stable leaving group than an OR minus, which is about the same. These are about the same. And again, NH2 minus is not a very good leaving group relative to O minus because O minus is more electronegative, right? Cl minus is big, right? So it's a better leaving group than OR minus. All those periodic trends we've done before. If you look down here, H minus and R minus, right? These are horrible leaving groups, right? H minus and R minus are super unstable, right? So those are not very good leaving groups. That's why these don't react in these substitutions. Kind of as we're working through this nomenclature stuff, another thing to remember, here's 3 different forms to draw a carboxylic acid. So here's a carboxyl group. That is just this essentially section right here to consider the carboxyl group. It contains the carbonyl and the OH for a carboxylic acid. Carboxyl groups can be drawn in different ways, COOH, CO2H. Right? Those are both, should recognize, and you see those as well. Some basic nomenclature for carboxylic acids. Up top, you have the systematic name and the common name. So systematic name is the IUPAC. That's actually one that kind of makes sense. Common names are things you just they're just known. So basically, it's back to methyl, ethyl, propyl, butane. Right? So methanoic acid, because there's 1 carbon involved, this is methanoic acid. Ethanoic acid has 2 carbons involved. Propanoic, 1, 2, 3 carbons involved, or 1, 2, 3 that way, and butanoic again. Acetic acid, you should know. Formic acid, you should know. Other than that, I'm not really interested in knowing the common names. Pentanoic, 1, 2, 3, 4, 5, right, and so on and so forth. I'm not worried about you knowing those. But make sure you do know formic and acetic. Alright, some basic nomenclature for carboxylic acids. The numbering, the systematic numbering, is 1, 2, 3, 4, 5, 6. So starting with the carboxyl group is the actual number 1 priority, so it has the highest priority. The other way they can number these is off of, if you consider, again, this the carboxyl group, whatever's off that is considered the alpha carbon. So you can see alpha, beta, gamma, delta, epsilon. So if this whole group right here is our carboxyl group, the thing attached to it is the alpha carbon. Right? So this is the whole group, and the alpha carbon is attached to it. So that's alpha, beta, gamma, delta, epsilon. Versus systematic, where there'd be 1 carbon is with the carbonyl part. So it's a little different. All right, now to take this a step further, how would we do it systematic versus common? Most people, I mean, again, you should be able to do both of these. I'm not going to make you know tons of Greek, but if we zoom in on some of these, if we look at some of these, the systematic, the numbering, right, would be 1, 2, 3, 4. So it's butanoic acid, because there's 4. That's the main chain. There's 4 of them, right? So butanoic, it's an acid, so butanoic acid, that's the carboxylate part. And off the second carbon is a methoxy. The common name, you could also go alpha methoxy butyric acid, but I'm not going to put a lot to that stuff. Do understand where alpha, beta, and gamma are at, what positions they are. But if I gave you this name, right here, or this name, you should be able to draw the structure. Hopefully that makes some sense. Again, if you do another example, 1, 2, 3, 4, 5, right? The bromines off the third carbon, or the beta carbon, as it were, the same idea. Incorporate some rings. This middle guy you should know already, that's benzoic acid. So carboxylic acid piece of a benzene ring, benzoic acid, or benzene carboxylic acid. Here, carboxylic acid, the substituent off of that would be cyclohexyl. So cyclohexane carboxylic acid. Carboxylic acid is the main part. Again, carboxylic acid is the main part, and this time there's 2 of them. Note how they're drawn differently. The COOH, remember they could also be drawn CO2H as well. Another carboxylic acid derivatives are the acid chlorides. So that is essentially if there's this piece is considered the acid chloride piece. A couple different ways to name these. There's the oil, so ethanoyl chloride. So note the oil piece kind of here. Right? There's 2 carbons, so ethanoyl chloride or acetyl chloride is a common name. Again, if it's a bromide, it's a bromide. So 1, 2, 3, 4, 5. So it's pentanoyl for 5, oil, bromide, and there's a 3-methyl off of it. If you have a ring, again, cyclopentane, cyclopentane, carbonyl, chloride. Right? Usually I don't have people name a lot of these, but just so if you see them. Alright, so moving along, we're going to name some esters now. So we're going to naming esters with the O8 ending, the 8 ending. That's our suffix here, the 8. Carbonyl oxygen, carboxyl oxygen with an R group off the end here. So we have an R group off the end. So let's look at one like this. So it's last acetate, a common one we've seen before. So the 8 here, we have a phenyl off the oxygen, and we have a 3-carbon piece, right? So we end up with the phenyl part off the oxygen first, propane 1, 2, 3, O8, right? So propanoate. So it's actually an O here in front. That's how we name it. So again, here we'd have the methyl piece, right? That's off the oxygen, so that's right there. We have the parent chain here now. So how many carbons is that? That would be 1, 2, 3, 4. So butanoate. And there's a bromine, 3-bromobutanate off of that. Some carboxylate salts. I mean, just remembering these, and this is a metal, sodium, potassium. How many pieces again? This is 1 carbon, methanoate. Right, sodium methanoate. By putting the sodium in front, we know that it's been deprotonated. Ethanoate, carboxylate. Usually we go by the carboxylates as well. A little more clear. Again, a carboxylate is a deprotonated carboxylic acid. Right, this came from carboxylic acid reacting, right, and getting water out and then a carboxylate out. And here's a couple biological examples of these things. But this is a carboxylate. Lactones, know a couple of these. These are interesting. These are going to use your, I like to use the common names for these actually. A little easier actually than the systematic names. So if we take the 6-membered ring here, again, let's circle the part that matters, right? And the alpha carbon, remember, is not the one attached to this oxygen. It's off of the whole group. So if the group I circled here is the whole group. We start off of the carbonyl carbon. So this is the alpha, beta, gamma, delta. So we call it delta lactone because this oxygen attaches back to the delta position. But we always start counting, right? We say alpha, beta, gamma, delta. And it's still delta lactone, but we got to indicate it's a methyl there as well. So the type of, this is a generic type of lactone. This is a gamma lactone because of alpha, beta, and then of course we have the gamma here. So it's a gamma lactone. Anything more than that, knowing if it's a delta, a gamma, or even a beta lactone, that's basically the amount I want you to know. You don't need to know all of this stuff up here. It's more confusing. So know the delta, the gamma, and the beta kind of lactones. All right, nomenclature of amides. Biggest thing here is very similar to the esters, where we have a thing off of, right? This is our amide portion. We have something off the nitrogen, right? We have this parent chain piece. So in this case, we say an N to indicate it's off the nitrogen. N-cyclohexyl, right? That's this piece. Or if we label this A, that's this portion. N-cyclohexyl. Propane, 1, 2, 3, propane. So that makes sense. Propane. Amide, right? So amide is the suffix here in this case. So now if we put more things on, so let's circle the amide part, right? So amide. What's off the nitrogen? Well, there's a methyl and an ethyl. So we say N-ethyl, E before M, N-methyl, pentane, because there's, again, 1, 2, 3, 4, 5. So pentane, 5, amide, N-methyl, N-ethyl. Here, again, if you have, now you have 2 ethyls off of the parent, which is an amide. So you say NN diethyl butanamide, because 1, 2, 3, 4. Nomenclature of lactams. So the cousin of a lactone is a cyclic ester. A lactam then is a cyclic amide. Again, I'm not going to ask you to know much more than can you identify something as a delta lactam, because it's alpha, beta, gamma, delta. Again, this is the amide portion. The nitrogen is attached to the delta carbon, so it's a delta lactam versus a gamma lactam, which is alpha, beta, and then a little gamma there, versus a beta lactam, which is alpha, beta, right? Beta referring to where the nitrogen is connected to which carbon is the beta carbon. So I want you to make sure you know delta, gamma, and beta lactams. Just know how to identify what they are. Not necessarily name the whole thing. Just know this bottom portion. Here are just some examples. I'm not going to really harp too much on knowing all of these. Phosgene is a diacid chloride, carbonic acid, right? So 2 OHs. A carbonate is 2 esters. A urea is 2 amides. A carbamic acid is an NH2 and an OH. And a carbamate is an H2OCH3. All right. So you should know what a urea is and a carbamate. Carbonate is a urea, and a carbamate. So I would say these are the 3 I want to make sure you know. A carbamate, amide and an ester. Urea, diamide. Carbonate, diester. All right, so done with nomenclature. Let's start talking about some of the actual reactivity about some of these carbonyl compounds, right? The C double bond O, right? The generic C double bond O. This is, what do we know? Some things we know. We know that this carbon is sp2 hybridized, right? We know the bond angles are 120, right? That's shown here. If we look at a molecular orbital picture, we can see a little bit more. We can see the bond angles that were between here to here is actually a 90-degree bond angle between the pi bond and these sp2 hybridized carbons, or sp2 hybridized orbitals. So if there are H's here, or actually doesn't really matter what's there. The biggest thing to remember is if you have a p orbital, you have an sp2, an sp2, an sp2. So an sp2 hybridized atom has a p and 3 sp2s. And the p orbital, of course, makes pi bonds, right? As shown here, these 2 pi. This is a 1 pi bond and a sigma bond between them. All right, so remembering sp2 hybridized, 1 pi bond, sp2 orbital, sp2 orbital, sp2 orbital, p orbital. If you go back one slide, you can remember, look, there's a negative charge, the plus charge, a negative and plus in this resonance form. What we were calling the non-carboxylic acid derivatives. So I'm just going to draw a ketone and I'm going to draw an aldehyde. And the difference here is something like an ester, right? An ester or a carboxylic acid or an amide, right? The group off of there, right? These groups, right? Whether or not they're good leaving groups has to do with whether, a lot of it has to do with whether or not they can do these resonance structures as well, right? Ketone and aldehydes cannot do resonance structures. That's another big difference between these acid derivatives and the ketone and aldehyde. Now, what does this resonance do if we're going to highlight the carbon of the carbonyl group? Right? That's the electrophilic site. So the more resonance you do, actually, makes it less reactive, right? It makes these carbonyls the less reactive carbon of the carbonyl. right? More resonance will actually make this less reactive. Right? So actually aldehydes and ketones oftentimes, aldehydes and ketones are more reactive than esters, acids, and amides. Right? At least at this carbon, right? If we're circling that carbon there. So resonance actually makes this less reactive at these carbons, right? Because of this resonance structure. So because of that, there's more of a it's a polar bond, right? So if you look here in alcohol, of course, because of it's really high boiling because of H bonding, right, with itself, hydrogen bonding, that OH. But now if you look at esters, these other ones, there's some interesting things going on here too. So I would highlight anything that can do hydrogen bonding, right? Carboxylic acid and its amide with NHs, super high boiling point, right? Nitrile appears to have a really high boiling point too. There must be some sort of, right, intermolecular force going on here. Obviously it's not hydrogen bonding in the nitrile's case, but still must be pretty strong. Then if you look at ketones and aldehydes, and ethers are real low, right? So they must have very low intermolecular forces, very weak ones. Alcohols are high because of H bonding. And then esters, acid chlorides, and aldehydes are all, these guys are kind of all in the same boat. They're polar, but they're not super polar, and boiling points around there. But you can think about resonance structures making them more, right? So the biggest thing is thinking about here is hydrogen bonding, right? If you can do hydrogen bonding, it increases your boiling point. You have stronger intermolecular forces. If you can do resonance, usually that increases your boiling point. Nitrile must have strong intermolecular forces because it has such a high boiling point as well. All right, so here's just showing a picture of that. So you can see the strong dipole interactions here. And here you see the nice hydrogen bonding dipole interactions also with an amide, right? So amides have really strong interactions, right? Because the nitrogen can donate electron density so well. So that resonance structure for an amide is much higher than it is for carboxylic acid or an ester because the nitrogen, less electronegative, right? A nitrogen is less electronegative, so it's more likely to do this resonance form because the nitrogen is more likely to donate its lone pairs in resonance, right? So you're going to see a lot more of that going on. So amides particularly have really high boiling points, and we're made up of amides, so that makes sense. We don't boil very easy, right? We have strong intermolecular interaction, so that's a good thing. Kind of a fun side note, you can see as you add carbons, right? Think about it, as you add carbons here in these fatty acids, more and more carbons, the boiling point, melting point goes up because you get more and more greasy. Kind of like thinking about us. You can think about unsaturated ones, so if you start putting alkenes or double bonds in there, you probably know cis fats are better for you, right? Because it's a cis alkene, it's going to be harder for these things to stack up, right? So saturated fats, you know, are bad, right? You can think about these all lining up on top of each other and clogging up your arteries. Unsaturated fats, the cis ones are better than the trans ones because the cis ones form like kinks, whereas the trans ones, you can see I'll put a double bond right there, you can stack those up again. So trans unsaturated fats are bad for you again because they're literally the molecules stack up and clog your arteries. So there's a bunch of other fancy ones here. Here's a nice picture. No double bonds, but you can think about how well these things could stack up, right? Versus this one has a little kink in it, has an alkene that's a cis alkene. These are going to be harder to form, to basically clog up your arteries. All right, excellent. So now we're on to really hitting point about the reactivity. So we talked about nomenclature, we've talked about bond angles, being sp2 hybridized. Now how does this actually work? So this is an sp2 hybridized carbon. We talked about doing substitutions of whatever Y is here, right? But we know we cannot do no SN2 reactions on sp2 carbons, right? None. So we're going to do a substitution. We're going to lose this. This is going to be substituted. But we're not going to do an SN2. We're going to do a different mechanism. So we know that this carbon of the carbonyl is delta plus, right? It's attached to the double bond oxygen, so that's a delta plus. So this is a good electrophile. That carbon's a good electrophile. So nucleophiles are going to attack there. But they can't attack and straight kick away the Y minus because the bond angles don't work. So we have to do a different mechanism here. What that mechanism is called is a addition elimination. So you first do an addition, right? We first add in right? Have a nucleophile attack the sp2 hybridized carbon, kick up the pi electrons. We form something called a tetrahedral intermediate. Notice the carbon here was sp2, and then it became sp3, so it's the addition. In this tetrahedral intermediate, now we have a choice. We have two things on there. Right? We can either get rid of Y or Z, or we can get rid of Y. And whichever one's a better leaving group is the one we're going to kick out. Right? So Y, in this case, is a better leaving group. So we added in, we went from sp2 to sp3, tetrahedral intermediate. The electrons in the oxygen, which they just got, came back down, kicked out the better leaving group, which was Y, and reformed the pi bond, hence the elimination part. Right? So this is the addition. Here's the elimination. Reform the pi bond, as those eliminations are. Right? Kick out the Y, and the better leaving group is gone. So again, they like to use the terms base, then reactant. Basically, don't stop and think about what this is an equilibrium process. So let's just circle Z minus and Y minus. Really depends on which one's more reactive. If Z minus is more reactive, right, it's going to want to react. So the reaction is going to go that way. Right? Z minus is going to attack, do the addition, form the going from sp2 to sp3 carbon, tetrahedral intermediate, kick out the better leaving group because Y is, in this case, less reactive. So it's more likely to sit there and be stable. And then we get the elimination. They use the term weak base. I just think you stop and think about what's more stable, right? What's a better leaving group? Is there resonance? Is one larger than the other? Which one can spread the charge better? Which one's more happy with the negative charge? Right? And I'll show a specific example in a second. So what can sometimes happen, right? Remember, these are equilibrium processes, so we can shift equilibrium. But if Z minus is essentially less reactive than Y minus, right? This reaction's not going to go very much, right? It's going to be, right? It's just going to kick back out. The Z minus will add in. We'll do the addition. We'll do the elimination, but we'll get back to the same thing we started with because Z minus is the better leaving group. If the two groups are similar, so let's say one's Cl minus and one's Br minus, right? Pretty similar. Br minus is probably a better leaving group. It's a little bigger. But we're not going to make a ton, right? If, let's say Z minus is chlorine and Y is bromine, right? Bromine, well, maybe we'll get 70% of this, but we're going to always end up with still with 30% of this, right? Just because the difference in reactivity between chlorine and bromine isn't that great, that sometimes we will kick out Z minus again and go back this way. Right, so we'll get a mixture of reactants and products. Right, so we really want to see the difference, right, essentially in that leaving group. Right? How can we shift equilibrium? Again, I just think of it as leaving groups. Don't worry about the basicity part. Right? Which one's more stable, right? If this was this was Cl minus and this was Br minus, right? Maybe a 70-30 ratio would be about right for them sitting there in the actual reaction mixture. So let me show you an actual problem here. Let's go through one where this will be the case. So let's say I start with an acid chloride, and I'm going to react it with, right, this is, of course, has all been in basic conditions with negative charges. On your class notes, we talk a lot about basic conditions, right? That's the first one we actually talk about. So an overall negative charge. So here the first step is we attack the electrophilic carbon of the carbonyl group. Electrons go up. These are all equilibrium arrows. We went from sp2 to sp3 now that carbon did. Balance my charge. Tetrahedral intermediate. Now you have a choice. Which one's the better leaving group? In this case, chlorine is the better leaving group. All right, so we'll take that and kick the chlorine out. We've remade the pi bond, so this is our elimination step. This was our addition step. Now we've turned what was an acid chloride into an ester with Cl minus. And again, now why would this happen? Well, Cl minus is more stable than O minus. That's why this would go. You can think of cases where it'd be less likely to. So let's say I have an amide. And I'm going to react this with I minus. Alright, so let's move this stuff up a little bit. With I minus. Now, I can just shrink that down actually now. Move that there. Again, I minus can attack. Right? But again, I minus is not great of a nucleophile, and amides are pretty stable because of the possible resonance, which I don't have drawn here because nitrogen is willing to do that. So let's say this equilibrium lies right really more towards the reactants. We get some of this. Right? We say we get some of this. But the likelihood, the best leaving group here still is, right? The best leaving group here actually is the I minus. So you actually just go back to what you started before. And really, if I redrew this, there'd only be a very, very small amount, right, of this actually happening where these electrons come down, we kick out what would be, right, it'd be a very small arrow, what would be essentially N minus, right? That won't be very stable at all. And if anything, it's just going to react and go backwards again and essentially repeat the process, right? So it does matter on how stable the nucleophile is and also how stable the leaving group is, right? All right, showing here a basic SN2 slide. Now don't be confused, we're not doing SN2 reactions. The point of this is, right, what bond do we usually break? We always usually break the weakest bond. So what's the weakest bond on a carbonyl group? Right? That, of course, is the pi bond. So that's the bond we want to break. Right, so what does it look like? Molecular orbitals. So if the pi bond, right, looks like this. Actually, I'm going to draw it a little even a little more pronounced. Let's get a little more pronounced with this. Let's make this make sense. Right, so there's a carbon and an oxygen. Where do you think most electrons are at in the pi bond? I would guess they'd be around the oxygen, so that should be a bigger orbital, a bigger lobe. The carbon has some, but just not as big, and this is pronounced, right? And that's where they're bonding, right? Most electrons in the pi bond, right, in the pi bond are over by the oxygen. So if we start looking down here at pi star, well, guess what? Where's the bigger lobe at now? Now the bigger lobe, of course, is by the delta plus carbon, right? Now if I want to break a pi bond, I need to put electrons in its pi star. And so here comes the nucleophile attacking the pi star, right? As they put electrons in that pi star, what happens to the pi bond? It, of course, breaks, right? So that's what they're trying to highlight here. All right, one thing I'm not oblivious to, the chlorine does have lone pairs, right? It can do resonance, but how likely is the chlorine to give up those lone pairs? Not very likely. That's the difference. Base, but I would say I minus is more stable than Br minus if you put those in here as well, right? You could think about where that leaving group hierarchy was before, but basically what this is saying is what are good leaving groups? What is the most stable thing, right? It's going to be hard to work backwards, right? N minus is not a good leaving group. O minus is not a good leaving group. Cl minus is, right? So what becomes most reactive? When we say reactive, we are talking about this carbon, right? We're talking about this carbon, right? Which carbon is most delta plus, right? Remember, these guys can all do resonance, right? They can do resonance of varying degrees. And resonance makes that carbon less reactive. Right? So it's easy to go turn acid chloride into an ester, but it's probably hard to turn an amide back into an acid chloride, right? It's easy to go downhill, right? Reactive to something less reactive. Hard to go something less reactive and make it something more reactive. Right? It's all about, right, how delta plus these carbons are and how good of a leaving group you have attached there. Again, just highlighting, remember, if you can do resonance, that's going to make this carbon less reactive, which is going to make this those acid derivative, carboxylic acid derivatives that can do resonance much less reactive, right? Again, overemphasizing here, the best leaving group when you're in the tetrahedral intermediate. Again, tet intermediate. Now you have a choice. These electrons are coming down. Which group is the best leaving group? Which one's going to be the most stable? That's the one you kick out most of the time. Now this is just kind of highlighting the mechanism I showed before, right? Now remember, this is not SN2. This is a addition elimination mechanism, right? We can't do SN2s on sp2 hybridized carbons. But if you look at this, the big difference here is this versus this. Which one is a more stable with a negative charge? The chlorine is, so this reaction will go forward. Whereas here, right, Cl minus, right, is pretty happy. And this is not that great of a leaving group, so there's going to be no reaction in this case. But again, not SN2, additional elimination. We need to have a better leaving group, or more stable products than reactants, or a better leaving group is also the way to say it. Reaction coordinate diagrams, kind of highlighting these things. I wouldn't worry too much about, right, the intermediates. That's not the important part. But if you look here, you have a less reactive, a more stable compound. So like say something like an amide for a starting material. So you have an amide for a starting material. That's pretty stable. That's not going to want to turn into a ester. Let's say you have an ester. You're going to be probably, you'll be able to turn that into an amide. But let's say you start out with an ester and want to turn it into a acid. Both of those are about the same, right? Amides are more stable, worse leaving group than an ester, so it'd be an uphill process, poor leaving group, right? Nitrogen would be a bad leaving group. Again, here an ester to an amide would be a downhill process. Esters are more reactive, have a better leaving group than an amide. Then an ester and a carboxylic acid are about the same. An OH minus and an OMe minus about the same reactivity. So that's what we can look at as a free edge diagram. And to wrap up, to emphasize this again, if you look here, obviously we have our nucleophile attack, the carbon of the carbonyl. So this would be the addition step. Right? We can't do SN2s on sp2 hybridized carbons. This is still sp2. Tetrahedral intermediate, so the tet intermediate. This carbon's now sp3. We kick out the better leaving group. Y minus must be more stable, right? Less reactive than the CHO3 minus. Right? And that's the negatively charged. We've done anything so far as negatively charged situation, adding to a carbonyl carbon. So what about the case if we're not using basic conditions? What if we're using neutral? So that means I don't have an overall plus or overall minus, but I'm overall neutral. What would happen if I take something like this and just put it in methanol? What is that going to look like, right? Again, the nucleophile attacks, adds to the carbon of the carbonyl group, which is delta plus, right? We are sp2 here, so this is the addition step. Now we're sp3 in that carbon. We have to look at what leaving groups are around. So when we say base here, I would assume base could just mean another molecule of methanol. This is usually, I would usually say this is the solvent. And that's usually the solvent. So let's just replace this guy with that. All right, so HB here would just be CH3. All right, so the solvent's kind of helping move that proton around. And now once you've been deprotonated, right, once the H has been taken off, right, because at this point, right here, this is still the best leaving group. It has a plus charge, right? Leaving groups with plus charge is really good. But taking that H off, now it changes things. Right? So we call this a proton transfer, and this is transferring to the solvent this time, which is this. Now, a tetrahedral intermediate, so tet and tet. Now we have a choice here, either Y or OCH3. In this case, Y is going to leave, and we eliminate the weaker base. So what I would say here is, let's pretend Y is just Cl minus. Let's pretend Y is Cl minus. So Y equals Cl. Y equals Cl, not Cl minus. Y minus equals Cl minus. and Y equals Cl, right? So in that case, Y, especially in this situation, is going to be a better leaving group. So just translate Y for that. All right, kind of moving along here, still thinking about esters. We've kind of focused in on esters. Now, esters with water, but notice here, HCl. So now we're going to be in acidic conditions. Right? Strong acids around. So that's going to make things a little bit different. So we'll talk about what's going to happen first, but again, this is called a hydrolysis reaction. Basically what that means is we're adding water to this. We're hydrolyzing it. Right? So the group we have here is going to be replaced with OH, leaving the alcohol. So we're going to hydrolyze this ester. So a hydrolysis reaction turns an ester into an acid. That's what a hydrolysis reaction is in this case. Ester to an acid. Another type of reaction with an ester and a acid in this case is something called a transesterification. This is essentially a do-si-do of esters, where we react an alcohol with an ester, and we get a new ester and a different alcohol. Right? Essentially, this piece and this piece are switching spots. So we call this a transesterification, turning an ester and one alcohol into a new ester and another alcohol. Now I'll show the mechanism for these again. Again, though, acidic conditions, strong acid, H plus is around, right? Another reaction would be an ester with an amine, right? We're going downhill again, right? Because an ester is more stable than an amide, right? We're made up of amides. That's more stable, right? And this again, this is just with some heat. Usually they have to add. I would hearken to say they're going to need some HCl to make this to go as well. So this is usually done in acidic conditions as well, and they call this aminolysis, but essentially turning an ester into an amide. Again, I'm going to show the mechanism now for all of these and how it will work. Let's take a look at what happens with some of these reactions. Let's take a look at that first one, that hydrolysis of an ester. So we're taking an ester and we're going to react it with some HCl, and the solvent really is water. We're going to end up with a carboxylic acid, and in this case, methanol. And I would hearken to say I think this HCl is a catalyst, so we got to regenerate that as well. First step, we need to identify the electrophile and nucleophile. So hopefully by now everybody knows we have HCl around our strong acid. That is always going to be my electrophile. And my nucleophile is actually going to be the lone pair on the ester, carbon to carbon oxygen. Now why this oxygen? That's because if you look at the resonance possibilities, all right, if I label this 1 and this 2 oxygen, if I start drawing the resonance structure with a lone pair, you'll see one oxygen, or oxygen 1, actually is more electron rich than oxygen 2. So that's why oxygen 1 acts like the nucleophile in all these cases. And it will be that way in any of these resonance forms. So this oxygen 1 in this case will be the nucleophile first. It's a good kind of side note to remember what's going on there. Okay, so the first step, we've protonated the oxygen. That's an equilibrium process. Now, why would we want to do that? All right, so what did that get us? Well, and Cl minus, and then a whole bunch of water floating around because water is a solvent. What this did, by protonating this oxygen, that made this carbon of the carbonyl here that much more delta plus. Right? We've polarized that bond even more by making this oxygen, right, have another bond there. It's not happy. That makes this carbon that much more delta plus. Now, Cl minus is a better nucleophile than water, but there's a ton of water around, so water is going to be the one that attacks. So this is that first step, addition step. Right, where we go from sp2 to sp3. We form that tetrahedral intermediate. OCH3. You got to make sure we balance our charge, get an overall plus charge, right, in acidic conditions. And the water still has the H on there, so that's a plus there. Now at this point, we're going to need to do something called a proton transfer. So now at this point, you can do that proton transfer I was just saying. And essentially what that means is, right, I can move the H here to there, because that's what I'm going to try to get rid of it. The book will show maybe another molecule of water doing that, and then there's another step. It's just more steps. You don't need to do it, in my opinion. It's kind of a lazy way to do it, but that's okay. Time sometimes is of the essence. And now what you've done is you've turned this part, right, the ester part, into a better leaving group. Right now here, right, this is still the best leaving group, but now this is a really good leaving group. So now when these electrons come down, this will get kicked out. And we have now, right, of course, balancing our charges. There's the acid, and we've made methanol. And the final step is regenerating our catalyst, and that gets us to our final product. Regenerate that H plus catalyst. New steps, this proton transfer, right? Shifting the proton around to wherever you want it to move to make one group a better leaving group. And of course, here's our elimination step as well. This proton transfer is a new step. Shifting that proton around. The book will show the solvent doing it. That's fine. It just takes another step in there. But you could just say proton transfer, have these electrons, whatever group you want to leave, take those that H. That'll now have the plus charge. Now it's a better leaving group. That'll leave. And make sure you regenerate catalyst at the end. Kind of a fun one to think about also, remember, is what leaving group's the best? Right? Why is this more reactive than this? Right? Remember, if this leaves, this can do this. These electrons here, right, are more stable. This molecule is more stable because it, of course, can do resonance, whereas this cannot do resonance. So be careful. This phenylacetate, that's a good leaving group because it can do resonance. So just because it's an OC doesn't mean it's not all the same, right? If you can do resonance, you, of course, are a better leaving group, more stable. Esters are pretty common things found. A lot of waxes, Bs, also a lot of our fatty acids, a lot of fragrances come from esters. Esters usually smell really good. So a lot of our taste, smell molecules come from that. Obviously, some of these long chain ones are part of fatty acids and beeswax, all sorts of things. Again, this is just now showing the book, emphasizing what I told you before about why this oxygen is the one that's protonated. It's because of it has the most electron density, and because of this resonance contributor, right? This oxygen, if we labeled them 1 and 2, oxygen 1, right? The resonance structure shows us oxygen 1 is more electron dense. That means that's more likely where the H is going to get attached to. Here is the text version of what I just showed you on a blank slide. A little different. In this case, what they do, I'll back out here a little bit. What they do, they show, right, the oxygen, the most electron-rich oxygen attacks the H, so it's an acid, right? Water attacks the now more delta plus carbon. This is right. Why do we add the acid? To make this carbon more electrophilic. Now they'll show, right, the tetrahedral intermediate, and this time they'll show a base, which basically I would say is just more water in the solution doing that. Right, so it's really just the water in the solution doing that, transferring that proton around. Once you've protonated that water, then it can be, the proton now can get moved to whatever group you want to have leave. Now you've turned the group you want to have leave into a better leaving group. That comes down. You regenerate the catalyst, which would be, you could think of B as Cl minus or water, right? HCl is a strong acid, so H3O plus is the same. Elimination, kick that out, regenerate the catalyst, you're good to go. Ester to carboxylic acid, hydrolysis. Right, again, these are equilibrium reactions. How would you drive equilibrium reactions? All right, because we said esters and acids are about the same energy levels, right? OCH3 is just about as good a group as OH, but if you add a lot more of the star material reagent, you can shift equilibrium, or you can get rid of one of the products. You could boil off the methanol, or you can add a lot of water and you shift equilibrium. For a transesterification, it's basically the same idea as before, except now we're doing this do-si-do, and we want this to be the good leaving group. So when we do the proton transfer, we want to put the H and make this have a plus charge. Again, we're doing this, right? Why do we protonate? Right? Why are we using these acid conditions versus the basic and neutral? This, when you protonate, this carbon, again, this carbon right here, becomes more delta plus, so more susceptible to a nucleophile attack. So it's a better electrophile. That's why we protonate it. All right, so the mechanism here, protonation makes things a better leaving group, right? As we have, when we have a plus charge on something, that's a better leaving group than something without a plus charge, right? So acid catalyzed can make it a better leaving group than with not having the acid. Just a little bit of a side note here. This is interesting. I want to show everybody. If we have a tert-butyl off here, we actually go through a different mechanism. We actually have an SN1, an internal SN1 take place. Now, why would we do that? As we protonate, right, a tertiary carbocation is very stable, so as these electrons break, those electrons go up. We get the carboxylic acid in one step. We make a tertiary carbocation, which then can get attacked. We get the tertiary alcohol. So it's a little different with the tertiary alkyl group, a different little mechanism there. It goes through an SN1. So now we're going to have, essentially I'm going to show you two ways to take an ester. Right, I've shown you ester in acidic conditions. Right, now it's catalyzed. Now I'm going to show you ester in a basic condition. Right, and this is all hydrolysis. Right, turning an ester into a carboxylic acid. So this step here, if we had OH minus, right, so now we're in basic conditions. Right, negative charges, attacks the electrophilic carbon of the carbonyl. Electrons go up. Tetrahedral intermediate. Now there's a choice here. I would say we can kick out the OCH3, and if we do that, we get to a carboxylic acid, which then can get immediately deprotonated, right? Deprotonated by what just came off, and we make methanol and this carboxylate. Now this is a really bad electrophile, right? This carbon here, you can see there's a minus charge here now. There's a lot of resonance. It's going to make that carbon not reactive, right? So that's just going to sit there, right? So once we make that, it's over. Right. Yes, at this point, right, OCH3 could come off, or OH could come off, but then it could always come back on. Essentially what happens is you attack here, kick out the OCH3, you make the carboxylic acid, and then the carboxylic acid actually acts like an acid, right, where this H gets removed by this strong base that you just kicked off. The big difference here is between this acidic condition, ester, to turn an ester into an acid, versus the basic condition to turn an ester into an acid. The acidic one's reversible. Note the arrows. Right? That's an equilibrium arrow. It can go back and forth, right? If I add a bunch of methanol, right, if I add a bunch of methanol here, I could shift it back this way. If I add a bunch of water, I could shift it this way. With the basic, it's a little different. Because you make this carboxylate, which is so unreactive, right, versus this plain carboxylic acid, right? Getting rid of this H makes all the difference in the world. That much more. That makes this carbon that much more not delta plus, not reactive. With NaOH, it's irreversible. It's also not catalyzed. Right? Acid is catalyzed. Right? You regenerate the HCl. This is not catalyzed. Right? It's a big difference. All right. Now, what if I want to do an ester to an ester? All right. So, what about this transesterification? So, ester to ester. Right. The first one we're going to learn about is in basic conditions. So, what do you think happens here? We know this works here. So I'm going to show the basic conditions, and then I'll also show the acidic conditions as well. So let's see, let's take that, let's do the basic one first, and we're going to do it in ethanol. And what's going to happen is, basic conditions are nucleophile, attacks the carbon of the carbonyl, that's delta plus. we get a tetrahedral intermediate, right? So this is that addition step. Add in O. Now we have a choice to make, and I'm going to kick out this one, right? Just because there's probably more of this floating around. Now that's a better leaving group. That we're just going to drive equilibrium that way. We're going to put a lot of this in there to help drive equilibrium. So that's this elimination step, of course. We went from sp3 back to sp2 now. And now we have the new ester plus that, right? And this is, of course, in basic conditions with a negative charge. This is that trans-esterification. Trans-esterification. Good. Now, what if we want to do this in acid? What would that look like? So let's shrink this guy down a little bit, put him over there. Now let's take a look. If I was going to take this exact same set of things, and now I'm going to do it in ethanol, but I'm going to use H+. Now the first step, the oxygen, the more electron-rich oxygen attacks. That's, of course, making the carbonyl carbon more delta plus. Right? That helps activate this carbon right there. Now, in this case, the solvent is going to play a role. The ethanol solvent is now going to be the nucleophile because we've made this carbon of the carbonyl more electrophilic. So now that can attack. Make this tetrahedral intermediate. Of course, this is that addition step. Tetrahedral intermediate. Balance our charge. There's a plus charge there. Now we're going to do that proton transfer we've talked about. Right? And you can draw the arrows. It's probably from an intermolecular process. The angles don't quite work out, but if you want to draw arrows, that helps. Make you see it better. Turn that other part into a better leaving group now. Right? Again, these are all equilibrium reactions. We can drive equilibrium by having, right, a lot of reagents around the star material, so form products. Now this next step, now we have a better leaving group. These electrons come down. The better leaving group leaves, the protonated one. We want to make sure we're always balancing our charges as we go. So now we've made the ethyl ester. We've also made methanol. And then the last step, we're going to regenerate our catalyst, right? And these transesterifications are also acid catalyzed, so we remake the H+. So that's the difference here between this acidic transesterification, which is catalyzed, versus the basic transesterification, which of course is not. Plus charges, minus charges. So finally, to wrap this kind of up, this is a nice, interesting discussion about how do we know this isn't an SN2 reaction? How do we know it's not a one-step? How do we know it's not SN2? How do we know it's an actual addition elimination step where we go through an sp2 to an sp3 back to an sp2? How do we know we add in and then eliminate? The way they've done this is that essentially they've labeled one of the oxygens in an ester. And this is all this means is essentially isotope labeling, right? So imagine that 18, so it has an oxygen with a couple extra neutrons, that's starred. If you did an SN2, essentially what that would mean, if you did an SN2, that this O18 would always be in the products within a hydroxyl, right? If you did an SN2, you would always have the O18, what I'm starring here, would always be in the products. But what they found out was that it wasn't, right? If we're doing an SN2, the O18 would have to be in the products, right? But it's not, and that's the key. And you can look through this little mechanism here. It's a nice little study here showing how the O18 sometimes can be the part that gets kicked out. And the O18 will actually not end up being in the final product ester, which indicates to us that an SN2 is not possible, right? So that's the kind of the nice little side story there. That's proof that, somewhat proof that tetrahedral intermediates form, because if it was an SN2, the O18 would always be in the final products with this starting material.